Once we understand customer needs, we can translate these into technical requirements. We can identify critical parameters to effectively manage these technical requirements. These critical parameters require a tolerance range aligned with the functional requirements of the product. Tolerance is the amount a parameter can be allowed to vary from the target on a component. Tolerance analysis is a key part of the Design for Six Sigma process. The target dimension is the ideal dimension and the basis for our variations. Tolerance defines the quantitative limits of acceptability for parts and assemblies, in essence, the upper and lower spec limits. Min-max tolerancing is based on the quantities we use to define the extreme limits of the gap. Root sum squares is a statistical method to establish system capability of multiple parts that combine to form the system. Along with customer expectations and process capability, tolerance analysis is a significant contributor toward the establishment of a robust design. Tolerance analysis has many benefits to the business. It improves the fit of components and therefore enhances product function. Exploring tolerances allows us to assess the sensitivity of the design at various levels of parameters. We can further optimize the design to meet customer needs and functional intent. Equipment capability can be better understood. This helps us qualify parts faster and target equipment with the best potential to produce parts per our design. We can also enjoy fewer tooling iterations. Costs will also be lowered in the form of reduced scrap, rework, and ergonomic concerns. Lower costs and quality issues enhance our market share. We can also realize fewer program delays due to the product and equipment redesigns. We use tolerance analysis to establish our system design based on customer needs. We also can use this approach to help us understand the contributors of variability based on magnitude and severity. This helps us find the optimal design based on the sensitivities observed as we vary parameters. Looking at a basic illustration, if we have an envelope that must contain 4 components, A1 through A4, to make these parts fit, we must have a gap greater than 0. Each component can be described statistically by a mean and a standard deviation. Our justification for statistical tolerancing results from the conservativeness of the min-max tolerancing. Min-max assumes all parts are at their extremes. Statistically speaking, this would be highly unlikely. Root sum of squares is based on the probability of a defect derived from the variation of the parts. It is less severe than min-max and delivers 3.4 defects for every 1 million opportunities for a Six Sigma design. When comparing traditional forms of tolerancing to statistical tolerancing, there are numerous trade-offs. While min-max is simple and does not require data, it is very conservative and could result in parts that do not fall within tolerancing requirements. Root sum of squares with process data does require a greater investment of resources, but it will result in optimized tolerances that are grounded in data and can be probabilistically tied to our efforts in meeting customer needs. Essentially, we must tolerance the system before we tolerance the components. Root sum of squares can also be based on drawing tolerances. While this will reduce tolerance requirements, it is not data-driven and more variable in its potential to produce tolerances that are either too liberal or too conservative.